Linear algebra is fundamental in computer science, impacting fields like graphics and machine learning. It's the mathematics of vectors, matrices, and linear transformations. Are you ready to dive into the key topics of linear algebra? Vectors are ordered lists of numbers representing magnitude and direction. Matrices are rectangular arrays of numbers used for data representation and transformations. Understanding vectors and matrices is crucial for computer graphics and machine learning. Scalar multiplication and matrix operations are key concepts. Let's explore how they form the basis of linear algebra. Matrix operations include addition, subtraction, and multiplication. The identity matrix acts like one in multiplication, while the inverse matrix undoes another matrix's effect. These operations are vital in image processing and neural networks. Transposing a matrix flips its rows and columns. Mastery of these operations is essential for computational tasks. The determinant is a scalar value derived from a square matrix. It indicates if a matrix is invertible and represents the area or volume scaling factor. Determinants are crucial in system solvability and graphics. A zero determinant means no unique solution exists. Let's delve into their significance in linear algebra. Vectors are linearly independent if no vector can be written as a combination of others. This concept is key for basis vectors and dimensionality reduction. In machine learning, it aids in feature selection and encoding schemes. Linear independence ensures efficient data representation. Discover its role in computational applications. A vector space is a set of vectors that can be added and scaled. Subspaces are subsets that also form vector spaces. They are used in abstract models and algorithms. Understanding these spaces helps in computational problem solving. Let's explore their significance in computer science. Eigenvectors only change in size, not direction, during transformations. The amount they scale is called the eigenvalue. They are used in tools like principal component analysis, Google PageRank, and facial recognition. Knowing about eigenvalues and eigenvectors is important for data compression, system behavior, and stability analysis. They help break down complex systems into simpler, understandable parts. Explore how they power real-world technology and smart data handling. Vectors and matrices are integral in data storage, graphics, and machine learning. Matrix multiplication powers neural networks and three-dimensional graphics. Inverse matrices solve equations and aid cryptography. Determinants test graphics transformations' stability. Linear independence enhances machine learning features. Eigenvalues and vectors are vital in data compression and ranking algorithms. Vectors have both magnitude and direction, represented as ordered lists. They can exist in two or more dimensions and describe quantities like motion, position, and force. Each entry in the list is called a component. And these components define how far and in what direction the vector points. Types include column, row, zero, unit, and position vectors. Column vectors are vertical lists, and row vectors are horizontal. Zero vectors have all components as zero and no direction. Unit vectors have a length of 1 and point in a specific direction. Position vectors show a location relative to the origin. Operations like addition and scalar multiplication are fundamental. Vectors can be added by combining corresponding components, and they can be multiplied by a number, called a scalar, to stretch or shrink them. These operations follow specific rules and are essential for solving equations and performing geometric transformations. Vectors are used to represent forces and machine learning data. In physics, they describe velocity, acceleration, and applied force. In machine learning, each data point can be treated as a vector in high-dimensional space, making it easier to compute similarities or train models. Understanding vectors is key to mastering linear algebra. They are the foundation for more advanced topics like matrix transformations, eigenvectors, and spaces. Learning how vectors behave leads to better understanding in fields such as engineering, physics, computer graphics, and artificial intelligence. Matrices are arrays of numbers arranged in rows and columns. Types include square, row, column, zero, identity, and diagonal matrices. Operations include addition, scalar multiplication, and transposition. Matrices solve systems of equations and represent data in machine learning. They are essential tools in computational mathematics. Vectors can be seen as special matrices with one row or column. Both are used to represent multidimensional data. Operations on vectors and matrices form the core of linear algebra. Understanding their relationship is crucial for data manipulation. Let's delve into their interconnected roles. Row reduction transforms matrices to echelon form using elementary operations. It's crucial for solving linear systems. Echelon form has leading entries to the right of previous rows. All entries below pivots are zeros. Mastery of this technique is essential for computational efficiency. Linear systems are solved by transforming them into matrix form. This allows multiple equations with several unknowns to be handled more efficiently. The system becomes a single matrix equation, making it easier to apply structured solution methods using linear algebra. The inverse matrix method applies if the matrix is invertible. In this case, solving the system involves multiplying both sides by the inverse of the coefficient matrix, leading directly to the values of the unknowns. This method works best when the matrix is square and non-singular. Gaussian elimination converts augmented matrices to row echelon form. It uses row operations to simplify the matrix step by step until it becomes easier to back substitute and find the solutions. This method is more flexible and works even when an inverse doesn't exist. Both methods are crucial for finding solutions. Depending on the problem, one might be more practical or efficient than the other, especially for large or complex systems. Understanding these techniques is vital for computational problem solving. They form the foundation for solving equations in engineering, physics, computer science, and data analysis. Mastering them supports efficient and accurate results in real-world applications. The determinant reveals a matrix's invertibility and solution uniqueness. It measures area or volume scaling and transformations. In linear algebra, it's key for eigenvalue analysis and orientation. Determinants assess stability in control systems. Their role extends beyond mere computation. Matrix decomposition breaks down matrices into simpler forms. Techniques include LU, QR, and Cholesky decompositions. They optimize computations and solve linear systems. Decomposition reveals matrix structure and efficiency. Explore how these techniques enhance computational tasks. LU decomposition expresses a matrix as a product of lower and upper triangular matrices. It's efficient for solving systems and reduces computational cost. LU is reused for multiple right-hand sides without recomputing. Understanding LU decomposition is crucial for computational efficiency. Let's explore its applications. QR decomposition uses orthogonal and upper triangular matrices. It's stable for solving least squares problems. Cholesky is efficient for symmetric positive definite matrices. Both decompositions are vital in numerical linear algebra. Understanding them aids in optimization and machine learning. Eigendecomposition involves diagonalizing matrices with eigenvalues and eigenvectors. Singular value decomposition, SVD, handles all matrix types. Both are crucial for data reduction and stability analysis. They reveal matrix rank and null space. Explore their significance in computational tasks. Jordan decomposition extends eigendecomposition for non-diagonalizable matrices. It breaks a matrix into a form involving Jordan blocks which group similar eigenvalues and include some structure for handling repeated roots. This is helpful when a matrix doesn't have enough linearly independent eigenvectors. Schur decomposition uses unitary and upper triangular matrices. It expresses any square matrix as a product involving a unitary matrix and an upper triangular matrix, where the eigenvalues appear on the diagonal. This form is numerically stable and useful in practical computations. Both are essential for eigenvalue computations. They allow us to understand the internal structure of a matrix. Even when standard diagonalization isn't possible, these methods are especially valuable in numerical linear algebra and advanced system analysis. Understanding these decompositions aids in stability analysis. They help predict long-term behavior of systems, such as whether solutions grow, decay, or remain stable over time. Let's delve into their computational roles. These tools are vital for solving differential equations, modeling dynamic systems, and analyzing matrix functions in engineering, physics, and machine learning. Different decompositions serve unique purposes. LU and Koleski enhance computational efficiency. Eigen and Jordan provide theoretical insights. SVD and QR are practical for data applications. Understanding these techniques is crucial for solving complex problems. Linear algebra is integral to computer science, impacting various fields. From solving equations to data compression, its applications are vast. Mastery of linear algebra techniques is essential for computational success. It's a powerful tool for analyzing and transforming data. Let's embrace its potential in technology. In conclusion, Jordan and Schur decompositions are powerful tools for understanding and simplifying complex matrices. They extend the reach of eigenvalue analysis to cases where standard diagonalization is not possible, offering deeper insights into matrix behavior and system dynamics. Their role is crucial in fields that rely on stability analysis and numerical computation. Thank you.